Okay, good evening, everyone, and welcome to our first session of our Escuela de Primavera, or Spring School in English. Um, Something new. We just started as a Catapa Colombia working group, and I see there's a lot of people I don't know, so I'm guessing a lot of you don't know what Catapa is. So I just will quickly explain it to you. Catapa is mainly a volunteer organization. Um, that works on a theme of mining in mostly Latin America, um, on different aspects. On one side, supporting local communities who are resisting against big mining companies, and on the other side, also in Europe, creating awareness around where metals come from, where minerals come from, what impact it has, and how we as people in Europe can take action against these big mining problems and conflicts. And so our spring school is about mining issues in Colombia, because as Catopa Colombia working group, we are all very much interested in what's happening right now and how we can get involved. But we also think it's important that more people know about what's happening. And that's why we chose some emblematic cases, which are the mining case in Jericho in the southeast, wait, yeah, southeast of Antioquia. It's really weird to say it in English. And then also we have the very famous case of Cajamarca, Tolima, and also the other famous case of Santurban in Santander. But before we start all of this, we want to know a bit more about why exactly these mining companies are coming to Colombia, and why the Andes Mountains. Um, like, what are they all about? How did they come to be? Um, and that's why today Laura Caicedo is going to explain to us more about it. It's geology for dummies, and she wanted me to actually confirm this again. So it's for us to understand more and to understand better, so that we can take more actions. But Laura herself is still also in a learning and an investigative process. She's actually a graduate from the geology in the La Universidad Ruiz of Santander, the public university. And now she has done, or she's doing actually, she's finishing a master here in Ghent in Belgium, and therefore she's now doing an investigation in Prague about massive extinction. That's how I understood it. But she will tell us lots more, so I won't keep speaking, and I give you the word to Lara, who is also, of course, I forgot to mention, Catapista and part of the Catapa Colombia working group. We're very, very grateful to have her here and to have you all here tonight to listen to her. So, Lara, go ahead.
Okay, thank you, Carlen, for the introduction and the welcome. And good night to everyone. Yeah, so as Carlen said, I will start with the spring school today, doing a brief workshop or talk about the history of the planet and the minerals in the Andes Mountains. I want to emphasize that I'm not an expert in minerals and in the Andes tectonics. I'm rather in other topics, but of course I'm geologist, so I can explain you the basics of how it works and why the Andes are so rich in minerals. So welcome everyone. If I speak too fast or I say some words that maybe you have not heard before, just feel free to ask. Um, and yeah, so I will start now. So I hope everyone is able to see the slides. I hope it's working. Okay. Okay, so this is the summary, the outline of what I'm going to talk today. I will start by talking about the Big Bang, the origin of the Earth. Then I will explain the Earth layers. Then I will talk about plate tectonics, plate boundaries. Then the life in the Earth, how it evolved, how it started, and how it is now. I will briefly mention extinctions, the big five mass extinctions that occurred in the Earth. um, then I will explain also briefly the geological setting of Colombia in the geological time. And then I will talk about a process that you will understand uh, um, afterwards, that is called the subduction. That is the process that gave origin to the Andes Mountains. Yeah. So let's start with the beginning of everything that was the Big Bang. And before talking about the Big Bang, I want to show this calendar. It is called the Cosmic Calendar. I don't know if maybe you heard about this before, or maybe you saw it in some TV program. Why? Because in all the presentation today, I will talk about the geological time scale, and it's somehow a bit abstract to talk in geological terms when we talk about time, because everything takes millions of years. Mountains, organisms, everything takes millions of years to be formed. So someone, I don't know who did this, but I saw it by the first time with a program of Carl Sagan, did this cosmic calendar, comparing how everything in the earth and in the universe was formed with the calendar we know, starting in January and finishing in December 31. So in the geological time scale, we know that the origin of the universe occurred 13 billion of years ago, or yeah, better say 13,000 million of years ago. So that's a very long time. It's very difficult to imagine, but that's how it is. Then 11 billion of years ago, we have the formation of the Milky Way, that is the galaxy in which our solar system is. And then we have the formation of the Earth, that was around 4.5 billion of years ago, or 4,500 million of years ago. So if we take all these strange numbers to the cosmic calendar, we have, yeah, like the first day, January the 1st, the Big Bang. Then we have the Milky Way somewhere here. And what is very interesting is that the last day of the normal calendar, that is December 31, is when humans appeared during the last minute or even during the last seconds of the calendar that we are seeing here. So it means that the time we have been in the earth, in comparison to the rest of organisms, or in comparison to the time that gave origin to the galaxies and solar system and the sun and the moon, our time as humans is somehow insignificant. It's very short, and it will be very short. Okay, so now I want to explain the earth layers. Why? Because this is the basic to understand how everything works in the earth. The earth is very dynamic, and thanks to the differences that we have in the different layers inside the earth, many things happen here at the surface. Um, so we have two ways to classify these layers. One is according to the chemistry composition of the layers, and the other one is according to the physical properties. So let's start by explaining the chemical composition. of these layers. So I will start from the surface and then I will go deep and deep up to the core. That is the deepest part of the Earth. So um, we have oceanic crust and we have continental crust. So the oceanic crust is basically what is lying under the ocean, and we have the continental crust. Yeah, that is what forms the continents. So basically, the oceanic crust is very homogeneous, is much heavier than the continental crust, and is much thinner than the continental crust. It is mainly composed by basalts that are volcanic rocks, and I will explain then how they are formed. And then the continental crust is more heterogeneous, and something very important to know is that the continental crust is much thicker than the oceanic crust because okay, how can I explain this? Yeah, imagine, for example, when you see an iceberg in the ocean, the part that you see above the water is just a small part of the iceberg. The rest of the iceberg is below the water, and it happens also with the mountains. So we see a part of the mountains, but let's imagine that the mountains have a kind of roots and we don't see them, but more than the half of the mountain mass is below the surface. So the continental crust is not the same everywhere. It is much thicker where there are mountains. For example, imagine in the Himalayas, we can have 40 kilometers or maybe um, more volume of continental crust. Then we have the mantle, that is a huge portion of the Earth, and in terms of chemical composition, it is mainly composed of magnesium and iron. Why? Because if we go deeper in the Earth, we have heavier elements. So metals are heavier than most of the elements that we know. So that's why these elements are more concentrated at the deeper parts of the Earth. So in the mantle, magnesium and iron, and this is a rock that that came from the mantle, but we have it at the surface, and then I will explain how is that possible. And then we have the core that is mainly composed by iron, nickel, and in less proportions, there is oxygen, silicium, and sulfur. So these are the layers according to the chemistry of the Earth. Then if we go to the physics, to the physical properties of the Earth, we have to take to consider that if we go deeper in the Earth, we have high temperature and high pressure. If you go deeper, you will have more temperature and more pressure, and more or less this gradient is about, I don't know, maybe at 100 kilometers of depth, we can have more than 1000 Celsius degrees. So it's very hot. But also because there is a lot of material above, we have a lot of pressure. So it's like a kind of competition between the temperature and pressure when we go deeper, and it changes completely the physical properties of the materials when we go deeper. So what happens, these changes make that the materials behave very differently. So if we are here in the lithosphere, we have a layer that is very rigid and rocky, but it's also fractured. But as it is, let's say, cold, the material is able to be solid. Then, if we go a bit deeper, we have this layer that is the asthenosphere, and is a weaker layer, and it behaves like a plastic, let's say. But this layer is not as hot as the ones that are below. So this material is not completely liquid. Uh, Thanks to the difference between these two layers, the lithosphere and the asthenosphere, it is possible to have tectonics in the earth, because imagine that you have a very solid material that is like kind of floating above a very weak and plastic material. So I don't know, let's imagine a cube with honey, and above we have some wood blocks, something like that. And these wood blocks move. It means that the lithosphere, this rigid and rocky material in the earth, moves. That's what tectonic plates theory states, but I will talk about that later. So yeah, then if we go deeper, we have the mesosphere. If we go deeper, we have the outer core that is liquid, but if we go deeper, we have the inner core that is solid. What happens here is that, yeah, we have high temperature and pressure, but here at the deepest part of the earth, the pressure is so high that, let's say, that winds to the temperature and the material is able to stay solid. So imagine that the inner core of the earth is a kind of sphere, a metallic sphere that also makes possible the magnetic field of the earth to exist. Yeah, so this is the earth inside. Now, how do you think that we know this? Well, we could think that maybe we extracted samples from the core and the mesosphere and everywhere, like in the book of Jules Verne, Journey to the Center of the Earth. Of course, no, that's not possible because, as I said, it's very hot, and the pressure is also really high. So I don't know what kind of uh, technological equipment we need to go there, but it's really unrealistic. So there are some evidences and direct evidences that allowed scientists to know all these things that I mentioned before. And one is because of the seismic waves, and basically we can get information from the earthquakes. So there are many detectors of waves all over the world, and waves behave differently when they travel through different materials. So it's not the same for a wave to travel in the water or to travel in the air, and so on. So as you know, the material of the earth is heterogeneous. So thanks to analyzing how these waves travel through the inner earth, we know that the earth is heterogeneous. So for example, as you see here, these red arrows just are traveling through this part of the earth. Some others are kind of refracting, and so on. So thanks to seismics, we know this. And these principles also work for geophysics, to know how to explore places to find oil, to find minerals. So everything is connected. So thanks to these things, we can look for minerals, we can look for oil, we can look for everything in the earth. Also, another evidence was because of the kimberlites, that are these rocks that contain diamonds. So we know that the conditions for diamonds to be formed are very high temperatures and very high pressures, and these are conditions that we don't have at surface, but we have diamonds at surface. So this is a proof somehow of how is the Earth inside. Also, the magnetic field, as I mentioned before, we have a magnetic field in the Earth. So the only way to have it is to have a metallic inner core. And another evidence is the meteorites, because they are mainly composed by iron and other elements that are not very abundant at surface. And we know that meteorites were also formed as the Earth and the planets were formed. So as we don't have too much iron at surface, we can think that the rest of the iron, the composition of iron that we see in the meteorites, has to be in the core, concentrated in the core. So that's how we get to know this. Okay, yeah. So now let's go to the interesting part, because from here onwards, we start to understand somehow how the mountains are formed, what happened with the mountains in the Earth, what happened with the Andes. So everything started with this guy, Alfred, I don't know how to pronounce, Wegener. He proposed a theory that was called the Continental Drift. And he said, okay, the Earth is divided in several plates in the ocean and in the continents, and they move. These plates move. They are moving around. We cannot see these movements because these movements are very slow. They are like millimeters per year or centimeters per year, so are not perceived by us. And he collected some evidences to support his theory. And one of the evidences was the finding of fossils that were found. The same fossils were found in South America, in Africa, that are continents that are now separated. Also, he found similar rocks in continents that are separated and also with the same age. He also compared the the coasts of the continents. For example, if you see South America and you see Africa, they fit like in a puzzle. And I don't remember what else he said, but he was an explorer. He went to Greenland many times in order to find evidences to prove his theory, but his theory was rejected because he was not able to explain what kind of mechanism was producing these movements. And also because all the evidences that he collected were from Europe, and for that time, the Geological Society was from United States, so they didn't understand too much about the geology of Europe. So so he did not succeed to prove that his theory was right. Many years happened, nothing happened with this theory, and all scientists were thinking that the Earth was just static, that continents didn't move and anything happened. But then after the wars and after we had more technology, especially technology that was suitable for studying the ocean, this guy who was from Canada was able to collect the evidences to prove that Alfred was right, and he did it studying the ocean floor. So this is the current map of the tectonic plates, and basically it's like having the Earth. Imagine that you have a baseball ball, and you see that it has some divisions, and that's what you see here. So we have here, for example, the Pacific plate, and the Pacific plate is divided in the Nazca plate. We have the South American plate, we have the Caribbean plate, North America, and all the plates that you see here. So as these plates are moving, these movements are responsible for the formation of oceans, for the formation of mountains, volcanoes, and all the physical features that we see at the surface of the Earth. Um, the mechanism responsible for moving these huge masses of either continent or ocean, it's somehow complex to explain, but I will try to do it briefly. Just imagine when you boil water, and when this fluid gets warmer, it's somehow lighter, so it comes to the shallower parts of the water that is boiling. So we have a kind of convection current that moves like this. So when it is hotter, it comes to the shallow parts, and then if it gets cold, it goes deeper. So it works like this. So it's like when you are boiling water and you have something solid inside that bucket of water, that thing is going to move thanks to these movements and thanks to these changes of temperature because of the heat. And this heat comes from the inner earth, because you know that it's very hot there inside. That's the basic of how tectonic plates works. Of course, it's more complex, but that's how it works, more or less. Okay, so now I'm going to explain plate boundaries. Um, this is very important to understand how the mountains are formed, also how the oceans, how the opening of the oceans occur, how the fragmentation of continents occur. So I will do my best to explain this, because it's not so easy. Sometimes I don't even remember how to do it. But yeah, we have divergent boundaries, and these boundaries, it means that the plates separate each other. So for example, we have here two continental plates, and they start to separate, and this is possible by extensional forces. So it's like, I don't know, you have a piece of paper and you do an extensional force to the piece of paper, so the piece of paper breaks up. So what happens when you break up a portion of continent? That you have the opening of an ocean, because the ocean and the seawater are heavier than the continental crust. So the continental crust is somehow like floating above the ocean. So when you break it, you will see what is below the continent, and that's ocean. So I don't know if you are familiar with the supercontinents that existed before, like Gondwana, Rodinia, Pangaea. They started to break up thanks to these extensional forces, and that's how the Atlantic Ocean was born. Yeah. When these things happen, many things occur. Mainly, there is the formation of the crust, and we have formation of fractures, we have formation of faults, and very special geological fractures. But also through these fractures, there is material that comes from very deep parts of the earth, and this material ascends through these faults, and this material brings many important things like minerals. Yeah, so this is what happens with the divergent boundaries. This is a very ideal model. Of course, believe me, this is much more complex, but yeah, this is more or less how it works. This is the Atlantic Ocean, and I just wanted to show you this photo and this this thing that I draw here. This is the Mid-Atlantic Oceanic Ridge, and these are the features you see from Google Earth, and these are kind of scars, let's say, of the ocean floor, and this is the consequence of the opening of the Atlantic Ocean. So what happens here is like South America separated from Africa, and a lot of material came, like you can see it here, and you can see this valley, Rift Valley. A lot of material from the deeper parts of the earth ascend, and that's also why the ocean floor is constantly renewed, because of this. And this is called the seafloor spreading. But it not only happens in the ocean, it also happens inside the continents. So for example, we can see here, this is the Rift Valley in Africa. So this part of Africa, of the continent, is breaking up because of the separation of plates. Someone is raising their hand.
Yes, it's me actually.
Yeah.
I just wondering, these extensive forces you said, like when they break open one of the plates,
Mm-hmm.
is it, what's what is the time frame you're talking about? Is it like something abrupt that happens, or is it something that's happening all the time?
No. These extensional forces, okay, everything that happens in the earth take a lot of time, take millions of years. So it's not something that you see, okay, we are here in Africa and you have a fragmentation of continent abruptly in seconds or days. We cannot even perceive these things. The only things that we can perceive are like in our time are, for example, the earthquakes or the volcanic eruptions, but not these things. As I mentioned before, the movements of the plates occur in terms of centimeters per year for the fastest ones and millimeter per year on average. So this is something that we cannot really perceive, but now we can do it with GPS. But of course, it's not like, oh, the plate is moving. I see the South American plate moving to the north. No, we cannot see it. These movements are very, very slow.
Okay, thank you.
Okay, someone else raised the hand. I don't know. I'm sorry if I don't see it. Okay.
No, no one did it. You can continue.
Okay. May I ask how much time has passed since I began? No.
Half an hour, so you have still time.
Okay. So I will speed up because I don't want to make this so long. Okay, then we have this other process, this other boundary, sorry, that is the convergent one, and it's the opposite of the one that I just explained. And the convergent boundary is when a plate collides with another plate. So we have more than one type of convergent boundaries. We can have two continental plates that collide each other, but I'm not going to talk about that. I'm just going to explain the one that maybe we are more interested in, that is the collision of the oceanic crust with the continental crust, because that's what happens with the Andes. So what happens here? We have an oceanic plate in the case of the Andes, is a portion of the Pacific Ocean in the east, and that plate is called the Nazca Plate. So this plate is colliding against the South American plate, and as I said before, the oceanic plates are much heavier than the continental ones. So what happens when something is heavier? It sinks. So this is what happens with the oceanic plate in a convergent boundary. It goes below the continental plate like this, like as you see here in this cross-sectional block diagram. And what you see here, subducting oceanic lithosphere, this is the oceanic crust. So at the beginning, the oceanic crust was there, normal. But then it started to go below and to go deeper. And as you know, if it goes deeper, here the temperature is much higher. So all this material that was before in a cold zone, let's say, is now melting. And everything melts here. And this process of collision release a lot of energy and also causes that the continental crust causes deformation on the continental crust. This deformation is like fractures and the famous geological faults that are basically fractures through the surface that have some depth, and these fractures are, let's say, channels that allow all the material that is here in the mantle to go up, to ascend to the surface. This is what happens. And also another thing that happens in this process of collision of plates is the formation of volcanoes, as you see here, or volcanic arcs, as we have in South America. So this is how the Andes were formed, more or less. Of course, it's much more difficult. And in Colombia, for example, there is not just one cordillera. You know that we have three, and all of them have a different story. They were lifted at different times, but yeah, this is like the general model about how it works. We have a third boundary that is the transform one, and we don't have separation or collision. We have lateral movement between one plate and another, and it can happen either in the ocean or in the continent. Okay. I made this question, but of course I already answered it. It was a question for you, but of course I mentioned it when I was explaining convergent boundaries. So it's already solved, but yeah, just for you to remind this. So the Andes are part of the convergent boundaries process. Okay, now I'm going to talk about the life in the earth that I think is pretty important for everyone. This is a topic that I like a lot, and I am studying some extinction event, a very small one, but anyway, extinction. I will try to do it shortly because it's a very wide topic. Yeah, so the origin of life is somehow controverted. We still don't know when it happened, but it is believed that it started, it's 3.8, not 3.5, 3.8 billion of years ago, or 3,800 million of years ago, Some fossils were found in Australia, and these fossils were believed to be algae, or yeah, they are cyanobacteria. And these organisms were indeed the first life that existed in the earth, and they did something very important for the evolution of earth, of life in the earth, and the evolution of the primitive atmosphere, because these organisms, they still exist. These organisms do photosynthesis, so they take the carbon dioxide from the atmosphere and they precipitate calcium carbonate, and these are the white bands that you see here in this fossil. This is not a fossil of cyanobacteria, it's rather a fossil of the cyanobacteria activity. It's a bit difficult, but yeah, that's it. But these fossils were then controverted. I think someone confronted these, these fossils in this investigation. They said that they were not cyanobacteria, that they were something else. I don't remember what. So I don't know what is happening now with this, but I know it was under debate for many years. I don't know how it is now. I have not read about it yet. Then we have the Akaran Fauna, and we have these fossils that you see here in the photo, a bit strange. Their classification, it's a bit controverted. Yeah, everything with the life in the earth and the fossils and the taxonomy and classification is very controverted, because people use different classifications, and working with the fossil record is very difficult because not all organisms are preserved. And as you know, the earth is very dynamic and the earth destroys many things. So it's not easy to find a complete fossil. For example, sometimes paleontologists have to work just with a piece of shell or of bone, or yeah. But yeah, we have the Akaran fauna, and these organisms are believed to be the first metazoans that are animals, the first animals. Of course, they were invertebrate and they were in the ocean. Everything started in the ocean. At this moment, we did not have continents, and also the atmosphere was very primitive. The levels of oxygen were not as we know them nowadays, and that's why the life was not so diverse, or that's why the organisms were not so complex or so fashioned as we know now. But then everything started to change. Then we have this period, the Paleozoic, that you see the name here. This was a great period because the life started to, let's say, radiate. So you see here this model of or reconstruction of the bottom of the sea. These were organisms that existed at this time, at the beginning of the Paleozoic, the Cambrian. And during this time, the geochemistry of the oceans and also of the atmosphere changed completely. It means that there were more nutrients available in the ocean for the organisms to have more food and to have more minerals to build their skeletons. So if you compare these animals with the ones that I showed before, these are really amazing. Maybe they are strange or maybe ugly, horrible, but they were amazing for that time. And these reconstructions were possible thanks to exceptional fossils that were found in the Burgess Shale of Canada. So were fossils that have most of the part of the original organism and it made possible to reconstruct of all these strange animals that existed at this period. That was like the first radiation of life in the earth, in the ocean, and these organisms lived at the bottom of the sea. Then we have another revolution, that is the Plankton Revolution, and during this time, this GOBE means Great Ordovician Biotic Radiation. I don't know what is the, I don't remember, but yeah, we have more diversity thanks to the available nutrients in the water. So we have, for example, this nautiloid. We have these are fossils of grapholiths. These are still invertebrates and in the ocean. But while there was a great revolution in the ocean, there was not a revolution, but we had the first plants in the continents. So with the first plants in the land, everything changed, because you know that plants do photosynthesis, and photosynthesis is a very important process in the earth in terms of the geochemical cycles. So we have many cycles in the earth: carbon cycle, the hydrological cycle, and everything has to do with photosynthesis. So everything changes. And when the chemical cycles in the earth change, also the diversity changes. And then, okay, this is a fossil of the first land plant. It is called Cooksonia, and this is a reconstruction of how the plant was. It was very different, very primitive, no leaves, no roots, not flowers, but it was a plant, and plants are very important in the earth. Then we have Tectonic Revolution. The swimmers, organisms in the ocean. So we have the first armored fishes and the first ammonites that we all know them. And these are the most famous fossils. Very beautiful. Afterwards, we have the first animals that venture from the sea to the continents, and we have the first amphibians and reptiles. And we have this period that is the Carboniferous, and it is called like this because during this period we have the first huge tropical forests and swamps. And this period is called like this because thanks to these swamps and tropical forests that were then decomposed, and after millions of years they converted into coal, and the coal that we use nowadays. That's why it is called Carboniferous. And of course, you can imagine that if we have more plants, we have more oxygen, more photosynthesis, a very intense carbon cycle. So many things started to change afterwards. Then we have the first mammals and the famous dinosaurs. Afterwards, we have the first plants with flowers and seeds, the first placental mammals, and then we have the dinosaurs extinction. The dinosaur extinction led to the radiation of mammals. So mammals were not so diverse and so dominant when they existed, they coexisted with the dinosaur, but after the extinction, they radiated a lot, and let's say that they were able to dominate some ecosystems. We have maybe the primate ancestor, the primates, that is something like this. I don't know what is that. And then at the very end, we have the humans. They are believed that we originated around 2 million of years ago. I'm not sure about this. And we also have these big mammals that existed during the Quaternary, Pleistocene, and Holocene, when there were many glaciations, yeah, glacial and interglacial periods, and we have this very, very big fauna, megafauna, it's how it is called, but some of them went extinct. And there is a theory indeed that states that this extinction of megafauna during this period was caused by the overhunting of prehistorical humans. But as everything is very controverted, some scientists said that it is not possible, but it is still debated. So what can we see from this short history of the life in the earth is that it took many millions of years for everything to change, and for having the first plant, the first flower, the first seed, the first fish, the first everything. And we are at the very, very end, like our appearance in the world by first time was very late, and yeah, in terms of time, a bit insignificant. But we have done many things in the earth, no matter that we have been a very short time. Okay, I will talk about this very, very shortly. We have big 5 mass extinctions in the earth. The first one occurred at this time 439 million of years ago. And then we have these others. The last one was the one of the dinosaurs that was caused by a bolide impact, meteorite impact. And yeah, what I want to say with extinctions is that, of course, many organisms die, not only fauna, also plants went extinct. And these extinctions were caused by, not by only one cause, there were more than one causes. And some of them were driven by changes in the geological setting. For example, fragmentation of continents or collision of continents. Why? Because when tectonic plates do their job, everything changes, the climate change. So you know that when we have mountains, the mountains affect the regional climate as acting as boundaries for, let's say, the moisture. And also if we have a flat land, it is drier, or if we are close to the sea level, the ecosystems are different. Everything depends on tectonic plates, because it is like kind of driving the climate, also the oceanic currents, and all the biogeochemical cycles in the earth that allow to organisms to have food and everything. Okay, these are the big 5 mass extinctions, but of course we have minor extinctions. It means that they were not so catastrophic, but anyway, extinctions. Now let's focus a bit in Colombia. So I forgot to write the source of these images. This is a very nice book that was written by some Colombian geologists and biologists. I think even this lady from Humboldt took part of this book. If you are interested in having it, I can give you the link to download it. It's for free, and it's a publication of the Humboldt Institute, and it's a great work for like all kind of public, and it is called Hace Tiempo, and it's about the geology and the diversity and the history of the diversity of the animals and the plants in Colombia. So we have the Ordovician period. You can read the numbers here, how much time ago this happened. And in the red square, you have the country. So at this period, we had this supercontinent that was Gondwana, and South America, part of South America was here, also Colombia, and part of it was flooded by the sea. Afterwards, in the Devonian, some million of years afterwards, we have the fragmentation of Gondwana, but we also have this continent, this supercontinent that had North America and also Europe, that we don't see it here, but it was here, that was somehow colliding with Gondwana. And this collision gave origin to Pangaea, that was another supercontinent. Yeah. Then almost 300 million of years afterwards, after the fragmentation of Pangaea, we have this configuration of the continents somehow more similar to the one that we have nowadays. But if you see here, we don't have the Panama Isthmus. North America was separated from South America. And most of South America was flooded by the sea. So the Andes were not yet there. But here, this oceanic plate started to collide against South America. So everything started somewhere here. I don't remember exactly the number, but it's somewhere in this period of time. So you can see here like a zoom in of what was happening at that time. So most of the country was flooded by the sea. And it was 100 million of years ago. Okay, then around 30 million of years afterwards, we have that only the northeast part of the country was flooded, but the rest was not. And during this time occurred the extinction of the dinosaurs. And as I said before, the tectonic that gave origin to the Andes started to work a bit before this period, this time. And let's say that the Andes started to form, not to lift, not to be at the surface as we see them now, because as I explained to Carlene, it takes millions of years, but everything started a bit before this. And we have the formation of some volcanoes that I will explain a bit, some minutes afterwards. And so this is the setting. And also this was a tree, Araucaria, that was very dominant in the forest of Colombia at that time.
Sorry to interrupt you. Which forest? Because there are several forests. Do you know which? In the Amazon jungle, in the Pacific jungle?
No, I don't know.
Or it's not really relevant. It was just.
Maybe it's relevant, but I don't really know in which parts. I would say like maybe at the places in which there was more moisture, maybe, or more carbon available for these tropical forests to exist. But I don't really know myself where they were. Okay. But I can have this in mind and maybe look for it in the books, in this book exactly, because maybe they mention it. Okay. Then we have this period, and during this period, the Paleocene, as I said before, these huge forests dominated great areas of the country. And if you remember, I talked about the first swamps and tropical forests in the earth. It occurred much more time before, during the Carboniferous, but it doesn't mean that those were the only forests that existed in the ancient times. Of course, there were many forests afterwards, and the position of the country of Colombia here was in the equator. So imagine that we have a very warm climate at that time that made possible to this forest to exist. And during this time, these forests were the ones that then decomposed to form the coal of the Cerrejón formation of the Guajira. And when the activities of these, some activities of this in the Cerrejón not started, I think it was much more time afterwards. There was a paleontologist, Edwin Caden, I think, that worked there, and they got to discover the biggest snake that existed in Colombia in that time, the Titanoboa. So you can see here how was the geological setting at that time, at the Paleocene. And you see that most of the country is not flooded anymore, as we saw it before. And as I said, the subduction or the collision of this oceanic plate against the South American continent already started and was active. So we have the formation of some volcanoes, and we have the process. Let's say we have the active process by which the Andes Mountains were formed. These red points that you see here, I will try to explain this with a diagram that you will see afterwards.
Laura, I'm just going to interrupt you that it's now 8:30, so I don't know. It's very interesting, but maybe if you try to speed it up a little bit.
Yeah, I'm close to finish.
Okay.
Yeah, I'm close to finish.
Don't worry.
Okay, so then we have this period 16 million of years ago, and again, the sea flooded a great part of the country. As you see here, the eastern Cordillera was completely flooded by the sea. So yeah, you can see a zoom in of this setting here. And we have this kind of very huge turtles at this time. And then this is like the current configuration of how everything looks nowadays with Colombia and the Andes. And you see also that North America was joined with South America. Okay, so I will play this video, it's just 30 seconds. You will see very shortly how the subduction works, because I think it's much easier like this if I explain it. Okay, so I'll pause it here to explain a bit what's happening. So this is the part of the oceanic crust that is colliding against the South American crust and is subducting. This is how it is called. And it's coming below the continental crust. And as you know, and I explained before, here it is much hotter, and all the material here starts to melt, and these forces give origin to the formation in this part of the continent that is the continental crust, is the South American continent So there is formation of many fractures and geological faults by which all the fluids here that are melted and are rich in elements like metals take these channels to come up to the surface. That's like the general model or the general explanation how it works, but of course it's much more complex. And what happened with the mountain, what happens is that imagine that when you compress something like, I don't know, your skin, you do this, you have a kind of mass that is compressed. So you have a higher volume of mass that is somehow lifting. That's what happens. It's by compressional forces how the Andes or how the mountains are formed. Also, we have formation of volcanoes because of this material that is magma that is inside the earth, has these channels to come to the surface. So that's we have also the formation of volcanoes and volcanic eruptions. And you know that the Andes are it's very common to have volcanic arcs and volcanic volcanoes through all the Andes in South America and Chile, and also earthquakes. These movements release a lot of energy, so that's why we have many earthquakes, especially in Chile, because that's where most of the motion, most of the movements occur. I'm sorry. Yeah. So I will, yeah.
Angela Riveros asks, part of South America was formerly water? Is her question.
Part of South America was formerly water, was flooded, was, okay, how would, was flooded, was covered by ocean. But saying like it was water, no, I would say covered by ocean water, as many of the continents that exist now. That's, for example, the reason why we see in the Eastern Cordillera some marine fossils, because it was part of the ocean. Okay, so I will finish with this diagram. So it's, yeah, mainly the same as you saw before in the video. And yeah, what I want to show here is what happens when the oceanic plate subducts, and as I explained before, the heavier elements of the earth are concentrated at deepest parts of the earth because they are heavier. So by gravity, the heaviest elements will sink because they weigh more. So how it is possible that these heavy elements, as the metals that are exploded nowadays in the Andes, in Colombia, gold, silver, copper, nickel, everything, how is it possible for them to come to the surface and to give us metals for all the things we use nowadays? It is possible by this process, but also by other processes that occur thanks to the tectonic plates. So this subduction model is just one of the models that explain how minerals are formed. There are many models to explain how minerals are formed. They are very complex, but this is just one example. So yeah, it's a very wide topic. There are even PhDs about this, and of course it's somehow difficult to cover everything in just one workshop, but I hope you understood the very basics, and yeah, that's it. These are the home messages. So life and resources in the earth take a very long time, and they undergo very complex complex processes to be formed. The diversity occurs because extinction also occurs. All organisms go extinct. Human time is very short, almost insignificant if compared with the geological time. And of course, you know, these resources are finite. And yeah, that's it. And thank you. If you have questions, you are welcome to ask. And I hope I can answer all your questions in case you have some. And thank you very much for listening to me today.
Maybe do you have any recommendations if people want to know more about, like you already talked about the book about maybe if you have any recommendations of things people can read or can watch or someone they can follow as to become more known on the topic.
I would say like for tectonics of the Andes and mineralization processes in Colombia or other countries in South America, the divulgation work, I don't know it. I know there is divulgation work more related to paleontology and the diversity of the ancient organisms in Colombia, and that's how this book that I mentioned was born. So I don't really know myself if there is material that you can read and understand about tectonics and mineralizations in Colombia or in the Andes, but I can have a look. I have to say that I looked for it, but I did not find, because it's pretty useful to do this kind of workshops, but I didn't find anything. Yeah, but of course, I highly recommend this other book that I mentioned. And if you want to download it, I can give you the link. I can send it in the group, or yeah, or you can write me directly.
I have a very short question.
Yeah.
Is it the same the same process happened for the development or the process of Andes? Is it the same for Alps, for the Alps mountains, or is it completely different?
Alps, I think is similar. It's a collision process of okay, let me think. The Alps, yeah, of oceanic plate and continental plate. But for example, it's different to the process that happened with the Himalayas, because the Himalayas were originated by the collision of two continental plates. So it's not always the same. It's not like mountains are formed because oceanic plate collides with continent. There is also collision of two continents.
And that might explain why the Himalayas are the highest one. Or that's not the case?
No, I wouldn't say like this is why.
Okay.
I think the Andes are still lifting, so they could be higher in the future. I don't know how much, but it depends on the intensity of the tectonic activity, and it depends, I think, I'm not sure, but I think it depends on the angle at which the oceanic plate goes under the water and some other factors.
Okay, Lisa Alvarado asks, do you know why certain minerals, for example, carbon, can be found in some places and not in others?
Yeah, of course. As I explained, carbon or coal, for example, when we know in Guajira, in Cerrejón, in the north of the country, this is the product of the decomposition of forests, of tropical forests. So for a tropical forest to exist, we need very specific conditions as some moisture, humidity, and temperature, very warm temperatures. And I think these conditions can be favored if we are very close to the equator, for example. So if we have these conditions, for example, if I have a continent that is located in the poles, of course, I wouldn't have a tropical forest. So I wouldn't have coal in the future at this place. So as I explained, in the Paleocene, this tropical forest existed in the country, and they gave origin to the coal that is exploded nowadays in the Guajira Desert in Colombia.
Okay, I don't see any more questions, but a lot of people are telling you thank you. They say, bueno, Diana says, gracias por toda la información y por tu tiempo y forma de explicar. Also, Lisa says, thank you very much. It was very well explained in an understandable way. I think that's a really good compliment because you wanted to make it for dummies. So
yeah. And it's not so easy. Sometimes it's more difficult that explaining it for colleagues or for the university.
Exactly. And Nora says also, thank you for the presentation. It was very clear and indeed nice to understand the geological processes. Yeah, and the rest, also other people, thank you very much. It was very clear and informative, and muchas gracias. And they're asking for the book, so I think we will look with Laura so that we put the link or the description of the book in the next email about the Escuela de Primavera, so that everyone has it. We will also send you all the recording. So some people, if they didn't manage to be here at the starting hour, like you can still watch it again from the beginning, and you can also share it with other people that are interested. Highly recommended. And I want to say a big thank you to Laura for being here today and for making a very complex theme a bit more understandable for the normal non-scientific people and also for others that are scientific. And I want to invite everyone to our next session, which will be about Jericho, which is a very important lucha struggle that is going on there at the moment. So I'm really recommending you all to assist and to tell other people, friends and family, to assist as well, because we think it's really important that more people know about what's happening in Colombia in terms of extractivism and the struggle against it. So everyone that's registered will get another email for next week. Also, if you cannot make it one session, it's okay to join a few, but we recommend you to assist all of them. So please tell it to all your friends and family, and thank you for being here, and enjoy your spring nights in the Escuela Primavera or spring school. Good night, everyone, and goodbye.
Bye.
Goodbye. Thank you.
Thank you, Laura.
Ciao, ciao.
Bye.
Da.